This is ITCAM 560, part 2 of 2 for logistic regression. Let's see where we left off. Where we left off is that we created the predicted probabilities of somebody being a cheater. They're right over here, predicted cheater. The question is that it's all good saying that, okay, this person has a 60%, 62% probability of being a cheater, but I want to be able to say, well, yes or no. Are they going to be a cheater, yes or no? So the question is, what's our cutoff? Is it at 0.5? Is it at 0.2? Is it at, well, the cutoff is going to be something that you can choose. And it is a judgment call. Many times when it's in terms of marketing, it's about a cost-benefit analysis that, the sum of all the people that are most likely to be the probability, let's say the probability of somebody buying is 62%, and if they buy $100. So the probability, your estimated revenue from this person, if they buy, they're going to buy $100. If their probability of buying is 0.62, the estimated amount for this person would be $62. The estimated amount for this person would be $11. If they buy, they're going to buy $100. Well, given that the probability of buying, if this were not cheater, but the probability of buying, it'd be 0.11, then, it's $11. So you have to say, well, this marketing endeavor, this marketing campaign, how much does it cost per person? If I'm only going to have $11 in revenue versus $62 in revenue, well, the question is, yes, so this person I would like to market to first, but how much does it cost to market? What is the profit on $11? If the cost to market is zero, then, well, what the heck, just market to everyone. But if the cost to market to someone is $1, and you're going to have revenue of $11, yet the profit, that's the question. So, there's a lot of considerations here. So that's where you start saying, well, what is my cutoff point? But here, let's just how do we choose a cutoff point? Again, this is a judgment call. I will show you a way that I'm thinking of starting to work for a judgment, for a cutoff point. So again, there is no right or wrong way in estimating a cutoff point. You just have to justify it in front of a group of people, of human beings that are going to say, wow, that sounds reasonable, or you know what, that's not reasonable, and they'll give you feedback, and it's up to you to incorporate their feedback in that, how to calculate that cutoff point. Okay, this is what I'm going to do. I'm going to say, well, what is the summary of this? Okay, well, the summary of predicted cheater, well, the median is 0.18, the mean is 0.22, the middle number is 0.18. Now, some of you may say, well, if the middle number is 0.18, well, anything above 0.18 is a cheater, anything below 0.18 is a cheater. Well, that means that in this data set, half will be labeled as cheaters, half will be labeled as non-cheaters. But this is not good enough for me, because the question is, in the data set, are half the people cheaters? Well, let's take a look how many cheaters there are. So I just do this, and this inserts into this object the sum of the variable cheater. Let's take a look at that variable cheater. Here it is, zeros and ones. So if I sum up this column cheater, it's going to give me the count of cheaters. There's 54 cheaters out of 195 observations. So it's much less than half the population. So look what I'm going to do here. I'm going to do this in steps. So I'm going to create my cutoff. If you want to see how you can do it in steps, just run this. And basically, cutoff, I've just inserted the data set val LR. Now, continuing, then I'm going to sort it in descending order by predicted cheater. Let's see how this goes. So let's look at our data set cutoff. And what have I done? Well, the highest probability of being a cheater is right up here, and the lowest probability is down here. Okay? So let's see why I did that. Well, so then the next thing is that I am going to filter the data where up to the row number is the number of cheaters. The number of cheaters is 54. So look at this. Basically, now I have a data set. Okay, I have filtered, the row number is row number 54. So look at this row number. I have the 54th observation where the probability is 0.27. If you want to see this again, how I got this, again, just remember this number, 0.276, and this was a male that was 37. Let's go back to our code without the filtering. I'm going to go to row number 54 now. Okay, I can see what row I'm at over here, or even over here. So row number 54, which is this one, I'm going to highlight it. Okay, it's a male that's 37, and their probability is 0.2765. Remember, there's 54 cheaters, so I'm going to get the 54 highest probabilities. And this is, out of the 54 highest probabilities, this here is the cutoff. Although there are some equal values right here, but it is what it is. That said, again, this is because of the prediction, all the other, remember, we're using years married, religiousness, and rating. They all have the same religiousness. They all have the same amount of years married, and rating and religiousness. So obviously they are going to have the same predicted value. Rambling on, again, let's go and do what I was doing before. I've just selected that row because I want to isolate this number as my cutoff point. So if I do this, again, I use cutoff, the variable predicted cheater, and if you see now, I'm going to just run this, I just isolated this value. Now that I've isolated this value, I'm creating this new variable called predicted cheater 01, saying that if predicted cheater is greater than or equal to the cutoff, this value over here, I'm going to give it a 1. And if not, it's going to have a 0. So let's run this. And let's do our summary. So it gives me 58 cheaters. Okay. I've just summed it up instead of 54. Close enough. And let's take a look at this data set. And again, I have my predicted cheater and I have my predicted cheater 01. Okay. Now we're going to be able to evaluate this model in terms that are easier to interpret as far as how good this model is. I'm loading my variable G models. We use this to do the chi-square test. We're not going to do a chi-square test. All we care about is this cross table. And take a look at this. Very interesting here, this cross table. We can interpret this because I have actual cheaters and predicted cheaters. So my accuracy is going to be along this diagonal. This is how I have it set up. So 0 zeros, that means I have a total of, how many non-cheaters do I have? 141. My model accurately predicted 106 of the non-cheaters, okay? We have our row percent here. 75% of the non-cheaters were accurately classified as non-cheaters. 24.8% of the non-cheaters were falsely accused of being cheaters. Now, we were able, this is the 1-1, we were able to accurately predict 23 of the cheaters. We were able to predict accurately 23 of the cheaters, 23 out of 54. Yet 31 of the cheaters, we predicted that they weren't cheaters. So it's up to you to decide, is this a good model? What do you want to do? Is this good enough? Do you want to if you want to play around with your cutoff point, again, where you gain accuracy, say over here, you are going to lose accuracy over here. So let's just say that I change my cutoff point to 0.66. Let's see what happens. And I run this. So I change my cutoff point, and now I am able to, of the people that are not cheaters, okay, 98.6% are classified as non-cheaters. 0.14 or 2 non-cheaters were accused of being cheaters. This is a error. We were able to capture 1 cheater, just 1. And 53 of the cheaters, we have labeled them as innocent. If we think about the US justice system, we say that we prefer to have many guilty be free rather than to incarcerate or find guilty somebody that is innocent. Well, unfortunately, here we have 2 innocent people, okay, are being accused of being a cheater. So again, what are the consequences of being labeled a cheater? Which model is better? This is up to you to decide later on. And it usually is in the case of our justice system, it is a moral issue. In the case of business, it is a business issue as far as, what are the dollars and cents implications to having errors either on the zeros or on the ones. So that's it for that. I personally, for this assignment, I would just leave it with, just choose one cutoff and that's fine. And again, then we'll be creating other models using the same data, but different algorithms. And we will be able to compare through this confusion matrix, that's what this is called, which model is actually performing better for what we intend to do. And that's it for logistic regression.